Hi everyone, my name's David and this talk is going to be about debugging large-scale Datalog. So as an introduction to the Datalog language, I thought I might go through a brief history. So Datalog is a logic programming language that was originally conceived in the 80s as a simpler variation of Prolog. Datalog was originally designed as a database query language, but SQL won out, and so Datalog was mostly dormant in the 90s. In the 2000s, however, Datalog had a bit of a resurgence with a number of different use cases. And these use cases tended to lead to Datalog specifications, which were much more complex than for database querying. One of the most successful applications of Datalog is static program analysis. So in the early days of Datalog as a static program analysis language, there was a flurry of development into a number of different specialized engines and frameworks. The problems with these early engines and frameworks were that they were quite limited. For example, the expressivity could only express certain types of static analysis. Furthermore, they often had issues with performance, and so they were mostly limited to being used for prototyping, where the developers would then go and create an actual static analysis in a language like C++ or Java. In more recent years, there's been further development into fast and high performance Datalog engines. So for instance, Soufflé can achieve performance that's even comparable to handcrafted analyses. There's also been other work looking into increasing the expressivity of Datalog, for example, the Flix project. So these modern Datalog engines have enabled large and complex static analyses frameworks, such as DOOP. So DOOP was originally developed in 2009, but since then has undergone a lot of changes so that it can take advantage of these modern Datalog engines. In addition to static analysis, there are a number of other complex use cases. For example, in binary disassembly, where the goal could be to check various properties of disassembled binary, Grammatic's Datalog disassembler tool contains a Datalog specification that's even more complex than DOOP. In networking, VMware has developed a Datalog-based tool called ddlog. And there have also been a number of projects looking at checking security properties, for example, in Ethereum smart contracts. And these properties are checked using complex Datalog specifications. So in all of these use cases, we see Datalog programs which contain hundreds or even thousands of complex Datalog rules. For a simpler example, this is a context and flow insensitive pointer analysis that's expressed as 4 Datalog rules. So these first 3 rules here will express relationships where variables may point to objects. So if we look at the second rule, for example, we say that if there is a variable assignment, so if var equals var2, and then if var2 may point to some object, then var may also point to that same object. The last rule expresses the alias relation. So if 2 variables may point to the same object, then they may alias with each other. So how we might use such a static analysis expressed in Datalog is, say we have a source program we wish to analyze. We can encode the source program as a set of input tuples. So here we see that each line in the source program becomes a single input tuple. Then we feed this input into our Datalog program, and then we get our set of output tuples. So the output tuples express the variable points to relation, and we can also see that the variable A may alias with the variable B. So this was obviously a very simple example of Datalog. But if we look at real-world analyses like DOOP, we see that DOOP contains 850 rules with really complex nested recursion. And for larger benchmarks, it can even produce outputs of over 1 billion tuples. So we need these modern fast Datalog engines which can handle these complex Datalog programs. But these modern engines mostly lack debugging facilities. So debugging these large complex Datalog programs can be quite challenging. Existing approaches don't usually scale too well, so a simple one could be to go and manually inspect the relations. But if we have relations that contain millions of tuples each, this might not work so well. There have also been a number of previous approaches where they look at derivations, so how the output tuples are derived from the inputs and the rules in the Datalog program. So Deutsch in 2015 and Lee in 2017 had two different approaches where they evaluate a Datalog program for a single debugging query. The problem there is that if we have a different debugging query, we would have to re-evaluate the whole Datalog program again, which can be quite expensive. Köhler in 2012 had a different approach where they store the full debugging information during the Datalog evaluation. Then afterwards you can go and query for whatever you like. The problem with that approach is that the full debugging information can be quite expensive, and so the experiments in that paper only go up to a few thousand tuples. So what we need is a debugging system which is succinct and easy to use, while also maintaining the high performance of modern Datalog engines. So our approach leverages a concept known as data provenance. The idea is we want to provide debugging information which is as succinct as possible, and this debugging information should explain the origins or the provenance of the results of the Datalog program in an on-demand fashion. So how this might look is we have a two-stage approach. So the first stage here is a Datalog evaluation, and we have an augmented Datalog evaluation that produces some provenance debugging information. And then after the evaluation is complete, we have an interactive provenance exploration phase. So here the user can query to explain whatever tuples they wish. Then the provenance generator uses these proof annotations along with the output to generate our provenance information. So for a more concrete example of what debugging might look like, let's imagine that one of our output tuples is incorrect. So this could indicate an issue with the Datalog rules, or even an issue in the input data. So the question is, how do we explain where this incorrect output comes from? So the form of provenance that we use is known as a proof tree. So a proof tree is essentially a description of how a tuple is derived from the inputs and the rules of the Datalog program. So if we have our query tuple, VPT, B, and L1, these are two different proof trees. So this illustrates that proof trees are not necessarily unique, but either of these proof trees is sufficient to explain why the output tuple, VPT, B, and L1, is produced by the Datalog program. So these proof trees form explanations for the output tuples. So the question becomes, how do we construct these proof trees? So to construct these proof trees, we could break down the problem into simpler subproblems. So let's say we want to compute one level of the proof tree at a time. So if we have our query tuple, in this case VPT, B, and L1, and let's say we know that the tuple is produced by the rule R2. The idea is we want to produce a subproof for the query tuple, which is essentially the next level up in a proof tree. So what this is just tuples that match the predicates in the body of the rule, so assign var and var2, and VPT, var2, and object, such that they generate our query tuple. So to visualize how this might look is we have our query tuple at the root of our proof tree. Then we want to generate the next level up in the proof tree. So I also wanted to illustrate that the whole proof tree should be of minimum height, because we wanted our debugging information to be as succinct as possible. So if we can solve this problem, if we can generate one level of a proof tree, then we can recursively apply it to the leaves of the proof tree. And then by doing this recursively, we can generate the whole proof tree. So the setup for this problem is we say that the Datalog program has already been evaluated. So therefore, the resulting output database is available, which means that all the tuples in the database have a derivation, since they have to be derived in some way by the original Datalog evaluation. So then the problem becomes, for some query tuple, we want to find a subproof amongst the resulting database. A naive approach for this problem could be to go and brute force search in our database to find tuples that could form a subproof. However, there are a number of problems for this. So the first one is we don't know which rule computed that tuple. And for complex Datalog queries, for complex Datalog programs, there could even be hundreds of rules computing a single relation. So to go through each of those could be very expensive. Second problem is the size of the data. So if we have millions of tuples, and if we have a big Datalog rule that has many predicates in the body, then there could be many different combinations of tuples that could form a proof tree. So it would be infeasible to try to go through all of those. The last problem is that there's no guarantee that the proof tree we produce is of minimal height. So we said that we wanted our debugging information to be as succinct as possible, and doing this naive approach does not give us any guarantees for the succinctness of the proof tree. So our main contribution in this paper is what we call a provenance evaluation strategy for Datalog. So how this works is, during the Datalog evaluation phase, we augment the tuples so that they store what we call proof annotations. So for each tuple, we have a number that represents the rule computing that tuple, and a number that represents the height of the minimal proof tree for that tuple. Then after the Datalog evaluation phase, there is an interactive system where the user can say, explain some tuple. Then the system should use these proof annotations to construct minimal height proof trees. Because this is an interactive system, the debugging information that the user gets is concise and understandable. Lastly, and perhaps most importantly, we can show that our provenance evaluation strategy has a minimal performance overhead. So for the first part of our approach, the augmented Datalog evaluation, so this is the part of the Datalog evaluation which takes the program and the input and then produces these proof annotations along with the output. So the idea here is we want to modify the Datalog evaluation system so that it can compute these annotations. So as I said before, for each tuple, we want a number which represents the rule producing the tuple, and a number representing the height of the minimal height proof tree. So for example, if we look at our VPT relation, we can see that the second tuple, for instance, this is produced by the rule R2, and it has a proof tree of height 2. So there could be different proof trees for the same tuple, but with a bigger height. But because we want the most succinct proof tree as a result, we store only the smallest height in our augmented database. So to compute these proof annotations, the first stage is we have to add 2 fields to each relation, so the rule number and the height. And then we need to instrument our Datalog rule so that they compute the correct values for these 2 fields. So if we take rule R2, for example, this is a rule that says if we have a variable assignment and var2 points to some object, then var can also point to that object. So we instrument this rule to become this. So the 2 here is just a constant that says this is rule R2. And the h here represents the height of this tuple. So the height is computed by the max of h1, which is the height of the first body tuple, and h2, which is the height of the second body tuple. So we take the max of the heights of the body and then add 1. Intuitively, how this works is that every time we evaluate a Datalog rule, we sort of add 1 level to the proof tree. So we take the smallest proof tree of the body and then we add 1 level to it. So this is max plus 1. So what happens if we have a smaller height tuple as computed later? So this is a problem that could happen because Datalog is stratified. So each stratum in a Datalog program consists of a set of relations which we compute to fixed point before moving on to the next stratum. So what could happen is that an earlier recursive stratum could compute a really large proof tree, And then in a later stratum, which could be recursive or non-recursive, it could compute a smaller proof tree. So how do we handle this situation? How do we handle if we have a smaller proof tree being computed later? The idea is we want to update the height annotation of an existing tuple. So to illustrate how this works, let's go through a standard Datalog evaluation first. So this is what we call the immediate consequence operator. And I here represents an instance, which is essentially a set of tuples. So in standard Datalog evaluation, in each round we apply our immediate consequence operator to our instance. And what this does is it takes all the tuples in the instance along with the rules in the Datalog program, and it attempts to compute as many tuples as it can using the original instance and the rules. So essentially what this immediate consequence operator does is it monotonically adds new tuples into our instance. So for our provenance evaluation, we have the instance as we had before, which is our set of tuples. And then we have h, which is a function mapping from the tuples into a height domain. So during our provenance evaluation, we also want some notion of an instance being smaller than another instance. So if we say this is our original instance, and then I prime and h prime is the resulting instance after applying some provenance consequence operator, then we say that the original instance is less than the resulting instance if the set of tuples in the original instance is a subset of the resulting set of tuples. So this is very similar to the standard Datalog, where for each application of the consequence operator, we monotonically grow our instance. But the second condition here is that the heights of the resulting instance are all less than the original heights. So intuitively what this means is that every time we apply our provenance consequence operator, we derive new tuples and we also reduce the height of existing tuples. So by doing this, we guarantee that once we reach a fixed point, so in this context, the fixed point means that we can generate that there are no more tuples we can generate, and also there are no more reductions in the height annotations that we can process. So at fixed point, we can guarantee that the height annotations of all the tuples are minimal. So there is, of course, a bit of a caveat, and the caveat is that doing this process increases the complexity of Datalog evaluation. So a common way of measuring the complexity of Datalog is by looking at the number of rule firings. So in standard Datalog, every time we evaluate a rule, we get a new tuple. So the number of tuples that we produce in a Datalog program is equal to the number of rule firings, since each rule produces one tuple. But with our provenance evaluation, a rule could fire and it could either produce a new tuple or it could update the height of an existing tuple. So in the worst case, if in each round the height annotation of a tuple is decreased by 1, then in the worst case we could have the maximum height number of updates. So in the worst case for a Datalog program would be the number of tuples multiplied by maximum height. However, this situation rarely occurs in practice. So it's very rare that we have a situation where an earlier derivation produces a larger proof tree than a later derivation. And so in practice, we observe that the performance overheads of our provenance evaluation is mostly fairly minimal. So at this point in this talk, we've seen how we compute these lightweight proof annotations. So for each tuple, we have a rule number and a minimal proof tree height. And we've seen how we augment the Datalog evaluation to compute them. So on to the second phase of our provenance strategy, which is the proof tree construction. So this is the part of the pipeline which is an interactive system, so the user can query and say explain some tuple. Then this provenance generator will use the proof annotations along with the output to produce proof trees. So how this works is we want to search for subproofs by using the proof annotations we computed earlier. So what this search for subproofs looks like is, say we have our query tuple, which is bpt b and l1, have our rule r2, and we know that the proof tree is of height 2. So we know the rule and the proof tree height from the annotations. So the idea is, again, we want to find a subproof. So we want to find tuples that match the body of the rule such that they produce our query tuple, and they also form the next level up in the proof tree. So in other words, they have a height of less than 2. So this problem can be expressed as a goal search. So here, for example, we have a goal that contains 2 predicates, which basically encodes the body of the rule. So we have that the variable var takes a value of b, which we know from our query tuple, and the variable object takes a value of l1. So we have the free variable var2, and we also have these 2 constraints that say that the heights of these tuples should be less than 2. So this goal can be seen as a form of a Datalog program, where the aim is to find tuples that satisfy these predicates, which is in contrast to a standard Datalog evaluation, where the aim is to try to generate as many new tuples as possible. So any solution for this goal would form a subproof. And note that the solutions to the goal might not be unique, so there might be many different combinations of tuples that form a subproof. But because of these 2 constraints, any solution will always be of minimal height. We also implemented our approach in the Soufflé Datalog engine. So Soufflé is a high-performance Datalog to C++ compiler that's been used in industry for a number of different complex Datalog applications. For example, we have DOOP, which is a pointer analysis framework for Java programs. We have DSLs, which is a binary disassembler that's built in Soufflé. We have Mad Max and GigaHorse, which are 2 different approaches to analyzing Ethereum smart contracts for security issues, and many other applications. So I'm going to give a very brief rundown of our implementation of provenance in Soufflé. So we have 2 stages which essentially follow the 2 phases of our provenance evaluation strategy. So the first stage is to augment the Datalog evaluation so that it computes the provenance annotations or the proof annotations. Then the second stage is our interactive system, where we use these proof annotations to construct proof trees of minimal height depending on the user interaction. So depending on what the user queries. To achieve this implementation, we had to extend a few core parts of Soufflé. So the first one is Soufflé's intermediate representation, where we needed a few new instructions so that we can achieve the updates that we require. And the second part is Soufflé's specialized B-tree data structure. So here again, we had to extend the B-tree so that we could update the height annotation of an existing tuple. Now we move on to the performance evaluation. So these 2 are 2 industrial sized benchmarks. So on the left here we have DOOP with the DaCapo benchmarks, and on the right we have the Datalog disassembler trying to disassemble binaries from the spec benchmarks. So we see that overall we have an overhead of about 1.3 times for the Datalog evaluation. So there are a couple of outliers here, and this is due to indexing issues in the Soufflé engine. But we observe that for the vast majority of benchmarks, the overhead is less than 2 times. So when it comes to actually constructing the proof tree, so I'd like to stress here that we can query for any tuple we like, because every tuple has these proof annotations. So to construct 1,000 nodes of a proof tree, this takes about 1 second. So to show how all of this works, this is our interactive interface. So the user here can say, explain some tuple, and the system will use the proof annotations to produce a fragment of the proof tree. Then the user can go and explore whichever other part of the proof tree, depending on what they think is the most relevant. So all of this is implemented and available in the Soufflé engine. So if you're interested, please come and check it out. So in conclusion, we've seen that real-world Datalog programs are becoming more and more complex. And as a result, debugging these large complex programs is becoming more and more challenging. So in this paper, we've introduced a new provenance evaluation strategy. So the first part of this provenance evaluation is an augmented Datalog evaluation where we compute these lightweight proof annotations. The second part is an interactive system where the user can query for proof trees. And we use these proof annotations to construct proof trees of minimal height. We've also implemented our approach in a real-world Datalog engine in Soufflé. And we've developed a user-friendly and interactive interface. And we've shown that the performance overheads for both Datalog evaluation and also for answering debugging queries, these overheads are more than acceptable for debugging purposes. Thank you.